high velocity bullet impact simulations aren't as simple as they seem. There's a hidden secret to making them accurate and most people get it wrong. But don't worry, you've got me to save the day. In this video, I'll show you exactly how to simulate a bullet passing through a plate the right way using Abaqus. So let's get right to it. Okay, open Abaqus, navigate to the part, create the part. First one is plate, deformable 3D. We want to have shell planar, and let's put this guy on 500. Continue. Let's create the plate here, 100 and 120. Scroll button. Now we have the plate. Let's create the sphere. This should be shell and revolution. Continue. Create something like this. It should be 10. Now with this guy, create lines. We create a line just like this. Then from here, auto trim. We trim this part. Scroll button. Done. 360 and okay, boom, we have the part. Okay, let's go to the property. Here the material property, general density, this is for steel, 78 E-9 as we have SI millimetric. And let's go to the mechanical properties, elasticity and elastic, 200 E3, 0.3 for the elastic. Let's go to plasticity and plastic. Here I have the material properties here and paste. Okay, now these are the material properties. Now let's create the sections. Sections must be shell homogeneous. One for plate with the thickness of 1, and we create one for the sphere with the thickness of 2. Now let's assign them. This one here, uncheck this one because we don't want to have too many sets. Done. This is a sphere. Okay, now we want to have the plate, this one, and plate. Okay, now the property is over. We can go to the assembly, create instance, select both of them, and the mesh must be independent because I want to mesh it all at once. And okay, now it's time to translate them. This one from here must be translated to here every time I click on scroll button. Okay, now it's time for the sphere. Zoom in a little. This should be center of the sphere. It should go to 100, 50 and 15. Then okay, if we look at it from the side view, we see there's a gap here because we want this sphere to hit this target with a speed. Let's put it back on this one, and the assembly is over. Let's go to the step. The step must be dynamic explicit. Continue. The time period must be 0.00 and 2. We don't need to change anything here, and okay. Now let's go to the field output. Let's go to the state. We go all the way down and we have a status here. As we want to see the failure, we need to toggle this on, and this interval should be 100 in order to capture every step. Okay, done. And we are done with this step. Let's go to the interaction. We need to create an interaction property because we want to have a contact between this one, the outer part of the sphere, to this side of the plate. Okay, so from here, create interaction properties, contact. We can have mechanical and normal behavior. It must be hard contact and allow separation after contact must be toggled on. Now let's go and create the interaction. From step initial, we can have general contact or even more accurate and better surface to surface contact. Continue, we select this sphere, down. Inside this sphere is purple and outside is brown, so we select brown. And surface for the second one, we select this one and done. It says brown or purple. If I rotate this, you see this side is purple and this side is brown, so I need to select the brown. And this should be finite sliding, interaction property 1 automatically selected and done. As you see, these squares, we make sure that the interaction is created. Now let's go to the load. We need to create a predefined field for the sphere, initial, mechanical, and velocity. Select this guy, done, negative 10,000 and negative 85,000, and V2 must be 0. Okay, the predefined field is created, so we created the spatial velocity. Now let's go to the boundary condition manager and create. We need to fix this plate. So from here, symmetry, continue. So we need to select the sides by holding shift and left click. We can select them, done, and cast because there's no movement on the plate. The load is also done. Now let's go to the mesh. Now we need to sit part. We select this one, done. Let's put it on 4.5 and OK. Then we select the sphere, done, 4.5 as well and OK. But we need to check the assign mesh control for the sphere. We can put it on quad dominated but medial. Now we click on mesh, select everything and done, and we have our mesh. But before we leave, we go to assign element type, select everything, done. We uncheck the reduce integration because we have a failure. We want to capture it in the most accurate way, so we need to uncheck this one, and this guy must be dynamic explicit. Okay, meshing is over. Let's go to the job. Here is where we define the shear failure. So we want to create the job. Let's name it shear failure and continue. Okay, we have to write the input file. We need to change something from the input file. So let's go here, shear failure, the IMP file. You can either double click on it, or if you're using Windows 10, you can go open with and select choose from another apps to select the notepad. I go for this one just once, and we need to define something here. By Control F, we can find the material. Let's go down until we find the material properties. Yes, here it is. This is the material properties. We have plastic. We need 1 star. So 1 star shear failure. This is not case sensitive, so you can either write it uppercase or lowercase. Press enter. 0.19. So here we define the shear failure. It means the strains higher than 0.19 would be subjected to failure. Now we need to save it. Done. Let's jump back to Abaqus to create a new job. Let's name it, for instance, crash element. And instead of model, we need to have input file, and here we need to select the shear failure INP. Continue. Okay. Now it's time to submit the job. Okay, let's monitor the job. Before the job being completed, if you've enjoyed this video so far, please let me know your thoughts in the comments down below. It's totally free for you, but it gives me the motivation to create more Abaqus tutorials for you. And there we go. Now let's go to the results. As you see, we have the element removal here. Let's see the animation. Yeah, it is so cool. We can also see it from different angles, such as this one, but we can rotate it to see that better. We also can slow it down a little. There we go. Now let's go and see the plastic strain. As you see, after it's done, we have values lower than 0.19, which was a failure criteria. But here, as you see, we have more values. Yep. When it reaches to that, it is going to subject to failure. Something else we can do is to plot velocity versus time. So we go to the XY data, ODB field output, continue. Let's put it on unique nodal. Here we have spatial velocity, put it on magnitude and edit selection. Let's have it on here. We select a point on the sphere and add selection, then plot. As you see, the velocity goes down like in Niagara Falls. With going forward, it means it loses the energy after it hits the target. You can also have the mesh sensitivity analysis in order to have the most accurate one. And with these values, velocity versus time, you would definitely see a convergence after a certain element size. That's it. If you enjoyed this video, smash the like button and subscribe. And if you want to learn tensile test simulation using damage for ductile material, click on the video on screen before it ends. Stay tuned.